tree-based, decision tree-based learning. That's one of the unsupervised learning topic, and we will learn the theoretical background to it. And at the end of the lecture, I have created one Jupyter Lab file for you to practice all we discussed, right? So it's in 19 slides, so we step by step go through that. So this outcome, basically learning, this is a learning outcome that you will be able to understand decision tree-based learning, principle of decision tree model, tree regularization, overfitting control, end-to-end supervised modeling process, and case study in a structured data application. And for case study, what I have selected is loan approval system. That is very easy to comprehend because we can all understand how loans are approved, and that includes your score, ranking, financial ranking, and then you have job, you have other stuff. So I'll go through that one by one. So this is one of the case study that we will do. So what is a tree and tree-based learning? As you can see in the picture of the tree here, that the decision tree is a flow chart like structured, right? So it's, if you have done if else, if this, do this, always there are two branches, right? Yeah. When there is a decision using if else, there's always two branches. That's just for somebody who has done programming. But if you look at the tree, they're always like, imagine tree has always two branches coming out of each branch, right? So you could make stop that decision on the top, or you could keep doing on next and next and next and next node. So the nodes are where the decisions are made. Okay. So for example, I'll give you a basic example that if you say if it is rain outside, take umbrella, right? If it is not rain, take sunglasses. Okay. And under sunglasses, you can have another decision. If you have eyesight problem, take prescription glasses. If you have no eyesight problem, take non-prescription glasses. Okay, so umbrella, and then this is a like tree-based decisions, and branches outcomes of those decisions. Like I said, that each branch of what is the decision in the example I gave you? If it is raining outside, right? Take umbrella. Okay, otherwise take sunglasses. So these are two branches coming out of the root decision. And then when you realize, I asked, it is not raining outside, right? Then you could do another decision. Is it sunny? If it's sunny, take sunglasses. If it's not sunny, take your prescription glasses, right? And then there could be another branch further up there. Are you going to a party? Take Ray-Ban glasses. If you are driving, take some other glasses. I don't know. I mean, just giving you some examples there. Now, going back to the so these are branches. Then you have leaves. Leaves is the where you stop. Okay. Finally, when you put the glasses on, right, going through those steps, that's your leaf. So how many leaves? If I say, count the leaves, all right? If it is raining, that's a root, right? Yes. Take umbrella. If otherwise, take glasses. Now the second leaf. If it's sunny, take sunglasses. Otherwise, take prescription glasses. This is a further leaf. There could be further leaf. Are you going to the party? Put your Ray-Ban glasses. Now put your normal glasses for driving. Okay? Something like that. So this way, like there are multiple leaves there. And you can decide how many leaves you want to put there. And these are actually, this is how in the Python you would be putting those terminologies there, right? So leaves mean, if you say I want a tree of 5 leaves, so you have to take the decision not more than 5 leaves. If there are only two leaves, it means you have to. I won't be telling you which glass is there. Pick glasses, that's it. You're on your own. Which glasses you're going to pick up? What is the probability that you will pick up? Now, from the perspective of training the model, right? If I say if it is raining outside, take umbrella. Else, take glasses. Now you have 3 types of glasses there. Yeah. Okay. Now, what is the probability of guessing? Are you going to take umbrella only with this one branch? One leaf. What is the probability of guessing that are you going to take umbrella No, not the bottom one. I'm just talking about the, are you going to take umbrella or glasses? 50-50, right? 50-50.
Yes.
But the probability of which glasses, if there are 3 or 4 glasses, yeah, probability goes really down, isn't it, for those glasses?
Yes.
And then you have to go to another leaf to get that probability right. So that is called calculating Gini, which I'll teach you today how to do that. And then finally, you draw that diagram. If alone, for example, for splitting the tree into multiple leaves and branches, and finally you get to the bottom of it, where you think, oh, Loon is proved or not, or which glasses have you wore, right? So let's move on to the next one here. Okay, so why decision tree? It's easy to interpret and visualize, right? And handle both numerical and categorical data. And both classification and regression can be performed with decision tree based algorithm. Right? And non-linear relationships are captured, and also basic assemblers methods are random forest, gradient boosting. These are assemblers for tree based. So previously we did SVM. SVM is not tree based. Last lecture we did SVM. SVM was support vector.
Yes.
And then we did a regression based one as well before that. So those are like different type of algorithm. Then there are tree based. Those are the one I showed you, random forest and gradient boost. So now, if you understand the impurities. For example, if I keep you on the top, right? Is your decision going to be pure? I don't think so, because if I say which glasses and I give you only one leaf, right? Your Gini calculation, which I'll explain you later, is going to be really, really high. If your Gini is 0, it means it's pure, which means now you can decide your probability will be really good. But if I keep you on the only one leaf, and if it is raining or not, and then I try, can I guess which glasses are you going to wear? Only that I know is it's not raining. Now can I guess which glasses are you going to wear? I need another parameter there, right?
Yes.
Is it sunny or not? Or not raining, is it sunny or not? Right? Then you can decide it's sunny, definitely you're going to get shades, right? If not sunny, you're going to get normal glasses. Stuff like that. So this is called impurity. Higher nodes, you have a higher impurity. If you go further down, you keep going down, down, down. These are called leaves. You keep doing, sorry, the, what was that? The term? Not the branches. The leaves.
Okay.
We did that here. No, leaf nodes, right? The multiple, you have root node, then you have a leaf node, then you keep splitting and going further down. And impurity is how mixed the classes are in the node. For example, if I said like only go on one leaf node, if it's raining or not, the classes are mixed for glasses. Which glass? Like, you don't know.
Yes.
But if I further filter it, that is sunny as well, then you know which one, right? So it's not mixed. So common measurement of, I think the most thing in the tree-based formula, what they do is they try and clear the impurity by looking at Gini impurity, and there's another way of entropy, information gain, and then the classification, calculating classification. These are the common measurement that we will do. So let's go through the Gini impurity. This is the formula for Gini, right? Where you calculate pi for each class and square it, then sum it, and then subtract it from 1. Right? So if I say only there are only 2 classes, what are the classes? Raining or not? How many classes are there? 2 classes, right?
Yes.
Yeah. So if only 2 classes, right? So I will do how many? What are the matrices that are saying it's going to rain? What are the matrices going to say it's not going to rain? Right? This is a root calculation. So if I say, if I have a data set on, let's say, loan, right? What will be the root class? How many proved and how many not proved? Forget about how they are proved. Yeah? The basic would be 2 classes,
Yes.
and I can calculate Gini by actually the number of classes, the 2 classes, right? And the pi is proportion of classes, I is the node, right? So first I will do the p square probability of first one p square, and then I square it, and then I plus it with another one, and then I minus it from this. I'll show you this how this is done on the next one. So these are the attributes I already explained to you: p square, I, purity, contribution of class I, and I'll explain you what is class, and the sum of p square is overall purity, and then we subtract it from 1, and that's where we get actually level of impurity. So if the impurity is 1, it's very mixed. If impurity is 0, it is very pure. So pure versus mixed. What do I mean by mixed? For example,
Like,
we don't know.
yeah, like
I mean, what it could be. There's so many things there. Right? That's mixed.
The probability is gonna be like,
Yeah. So we need to get the purity, which means we sort of filter it to a level where it is very pure. So let's give you an example here. This is a approved column. We have a lone data set, right, which has multiple nodes. So let me actually show you the data set first. I should have put this on that thing, but I think I got it here for you. This is the data set. I'll give you this file, by the way, and it's very well commented, right? And the lecture is actually from this file. So if we generated the lone data sets ourselves, 1000 lone values. I need to actually show you just a sec. I need to stop this PPT here. Okay, so here we are. So this data set approved in a column. There are 8. Let's say there are 8 samples, right? And maximum impurity, if we equally split them, 4 and 4. Okay, 4 approved and 4 not approved. Okay, imagine that. This is we're not talking about 1000 years. We're just talking about 8. Out of 8, and we just want to go on the root branch, which is basically, I mean, we got, let's say, 1000. How many are approved? How many are not approved? If we have 8, how many are approved and how many are not approved? So out of the 4 approved or 4 not approved, what is the probability? 0.5, 0.5. Right? 50% probability on both sides.
yes.
Right. So what we do is to calculate Gini, as I explained you in the previous thing here, as you can see the formula here. Sorry, I need to go back. Yeah. So to do the Gini, you need to actually take the pi square root, right?
Yes.
Probability square root of both, and make the sum of it and minus it from 0, which is very easy. We took the square root of probability, right, and minus it from 1 to 2.5 here. Add them together is 0.5, and 1 minus 0.5, 0.5. That's your Gini calculation, right? This is something you're supposed to do on the D-Day, right? Okay, so this is Gini calculation which you calculate. So it looks like it's quite mixed data. It's not very low Gini, is it, right? It's a mixed data, right? So we can't really tell from approved and not approved the next one will be approved or not, right? What we need to do is we need to decision tree use Gini, right? And how it does it calculates Gini for parent node, which we just did. What is the parent node, approved or not approved, right? And then split the data on feature. So what is the next? Those who are approved, why they are approved? Then we pick up the first feature. What their score greater than this? Then we go to another feature. We keep going bottom until our Gini is close to 0, right? And we consider all those features. And calculate the weight Gini of child nodes. So how many child nodes they become, like, depends on how many leaves we go further down, how many steps we go further down. And choose feature and split that to minimize the impurities. We keep going further down. So these are the 4 steps we need to do. So this is a formula to calculate our Gini, which I just explained, the top one, Gini impurity, right? Measure the impurity of a node. The second is weighted Gini. This is something I'll explain in the next one. I do that. And also Gini gain, and then maximizing the weighted Gini, right? Minimizing the weighted Gini. So we need to purpose is that you go to a level down where your Gini is close to 0. That's where you stop. The decision tree stops splitting the decision based on that. Now let's move on again, and so in the remaining lecture, my whole lecture would be based on these factors. So you need to understand these 1, 2, 3, 4, right? So let's go again. I'll try and explain this. So imagine our first step is based on our data set, and I'm going to show you the data set again, right? I'm going to show you the data set again here. This is our data set. This is our data set. Sorry, just a sec. This is our data set, right? So in this data set, we have 1,000 loan applications, right? How many loan applications? 1,000. And we generated that data set. And this is very documented. Explained to you how the data set is generated. So this whole area is just to generate the data set. Nothing else is there, right? And when we generated the data set and we put there here how many samples? 1,000 samples, right? And the data set is generated like this. So now on this 1,000 data set, what we're going to do is, first thing I'm going to pick up, it's got a multiple columns: age, income score, credit score, loan amount, and these are the application of loan. Those were made and based on personal circumstances of a person, married, not married, education, and has been defaulted or not, and a loan is approved or not approved. So if we want to, in a decision tree, if we want to calculate the first node, first thing we need to do is we need to actually split it on a root decision. What is a root decision? If you have 1,000 node, 1,000 application, what is it like? How do we split on the root? Approved and not approved. Forget about everything else. I mean, at the end of the day, you are trying to basically train a model that can predict the future application, right? So what will be our outcome? Either you're going to approve it or reject it, right? So that's your root decision, isn't it? That you're going to take. So whatever data set you have, the first thing you do is split it on the root. You won't do that. Actually, the algorithm will do that. So I'm explaining how the algorithm will work on that. So let's go back there. We go back to the lecture again, and here we are. So if we look at those applications, right? We have 900. Let's say, suppose our training data set has 930 applications approved, and these are not 1,000, by the way. These are more than 1,000, right? And 570 rejected. Okay. So what portion of those is approved? 62%. What portion of those are rejected? 38%. So it's a similar way that out of 1,000 there are 388 and rest are approved. So this data set is combined, right? So this is not the data set I'm talking about. I'm just hypothetically explaining. Imagine these are the number of total records we have. And Gini for the root would be, and we explained earlier that Gini for the root is that you basically have 3 parameters there to calculate the Gini, and Gini is the basic thing that you need to calculate for each decision that you make. The first is number of classes. So how many classes we have? 2, right? What is approved and not approved, right? And proportion of class I in node. So basically P probability square, right, of the class in the root. So what is the probability of those applications getting approved? 62. So you take the square root of 62, right? And then you take the square root of 38, right? And you minus it from 1. And that gives you what? Gini. So what is the Gini on the first branch? 0.47. That's the Gini on the first branch, right? Here, as you can see that. Now, if we, and if we look at it, what would happen is the first branch, I hope I have this here, right? The first branch would be actually calculated something like that, right? So if we look at the, this is your root, right? Because it's a DC tree, right? Okay, so you will have here the first branch based on approved and not approved, and then based on those are approved. So where are you going to put the approved and not approved? This is where your Gini is based on approved and not approved. But this is not giving anything, is it? Right? So then you pick up the second branch. Out of those, okay, you split them into how many are those? Those are now, when you say Gini is around 48% for approved and not approved, right? So you have a mixed data, which means you have a mixed data that you need to consider. Some of those are approved, some are not approved. You can't really tell. So the second layer you do is you say, let's look at their credit score. Okay? Anybody whose credit score is above 650, it comes on the right side, and right side is approved. But from that 600, and you are assuming that would be approved. But because the Gini is quite high, so maybe anybody who has 650 also have a data which is rejected as well, right? It's possible. And you say remaining come on the left side. So this is left, this is right. Okay. So this is your second, this is your first root leaf, this is your first leaf. Now when you come here, you calculate your Gini again. If your Gini comes 0, which means on the right side, if you do greater than 650, and your Gini calculated as 0, which means all of them are approved, right? And if your Gini is not 0, which means even filtering by 650, you would still have some rejected and some approved. So this is your second. So let's see here, if we look at here on the second leaf, how many comes on the left? I mean, if you split them by 650 credit score, okay, and you say greater than 60 are and less than 60. So if greater than 60 goes on the right side, right, of the, sorry, I need to do this, keep coming back. Greater than 60, if the greater than 60 is on the right side, right, here, this is a branch. Here we already, last slide we calculated the Gini here, based on approved and disapproved. Now we are calculating based on what? Greater than 600. So if this is greater than 600 on the right, this one, how many are there total? On the right? 870. And on the left, how many are there? 630. So out of those 870 on the right, how many are rejected?
200.
And how many are approved?
670.
Yeah, we still have mixed class there, isn't it? Right? Then it means that we need to first calculate the Gini and then move to the next leaf, right? And we keep doing that until we reach the 0. So let's go on the next one. Now, after splitting, I calculated the Gini, right? And this is PI1 and PI0. So there are two classes only, right? So for left side, right, there are mixed rejected and approved. So 41% on the left side are approved, right?
Yes.
Yeah. Yeah. And 59 are rejected. What is 59 rejected? 370. So if I put this into the Gini formula, right, I can calculate the Gini for left side, and for the right side, 77% are approved and 23% are rejected, right?
Yes.
And for that one, I need to calculate the Gini weight. So how do I calculate the Gini weight? I actually first split them into calculate the Gini. Now this Gini is not calculated using this formula. This is how you calculate the weight on the child node. Now there was a root node, right? There was a root node on top, and then you have a first child node, right? Left and right. These are the first child node, and left is this one and right is this one, right? So you need to calculate the Gini, same formula, and you know the formula, right? You take the root square of this, right, and take a root square of this, right, add them together, and minus them from 1, right? You minus them from 1. Where this is coming from? This is coming from here. This is coming from this Gini formula, right? So you have 1, right? And whatever the probability is, for example, approved 41, rejected, and that's on the left side. And the Gini is calculated on the left side. Sum of both probabilities and take the square of it, right? Take the square of the probabilities, take the square of this, take the square of this, add them together and minus them from 1, and you get this value, right? And this is how you calculated the value there. This is obviously going to be used by you, so you can talk in the recording, no problem, right? But I have to be quiet, okay? Because the recording is for the class. It's not going to get me a lot of.
You're publishing?
I'm publishing, but I was thinking like making it more discreet for other next time class. But okay, fine, we are done with that. That ship is sailed. Anyway, so you understand the top one, right? By the way, those came late. We are doing the C entry today, and the C entry is done by the top to bottom. So, for example, I'll give you another example of the C entry. And we'll be doing the C entry based algorithms. So the way the C entry works is very simple. It basically, if I ask you the root decision, it is raining, where take the umbrella. It's not raining, where the glass is. No, it's raining, take the umbrella. Not raining, where the glass is. Now, if it is raining, the probability of glasses, based on that decision, right? What is the probability of finding, and the glasses are 3 types of glasses. There are shaded glasses, non-shaded glasses. 2 types, let's say, right? So if it is raining, what is the probability of guessing the umbrella? 50%? It's raining or not raining. But probability of glasses becomes less than 50%. But if it's not raining, then you need to find out if it's sunny or not. If it's sunny, shade glasses. If it's not sunny, clear glasses. Right? 50-50 further down. So that goes down to further down 25-25. So shade and non-shade glasses probability 25-25. So this way you keep going to the branches further down. So if you calculate the Gini on top, you'll get a little 25 square root plus 50% square root. You get really low Gini on top. But then the second layer you get a lower Gini. So the whole purpose is to bring the Gini to 0. When your Gini is really, really down, right? When your Gini is down, that is where your algorithm will stop working. So what I'm explaining to you, obviously you don't have to do this manually, right? You need to understand how the algorithm works. Which algorithm we're talking about here? Any decision tree based algorithm. So random SVM is not a decision tree based algorithm, which we did in the last class. That is based on support vector.
Yes.
This is the random forest is a decision tree based, right? Gradient boost is decision tree based. So that's how those work. So now what we're doing is we need to, there are 3 steps. First you find out Gini of all the leaves, then you find weight for each child, okay, and then finally the third step, I'll come to that and explain. So how do you calculate the weight? Is very, very simple. This is a formula here, right? You basically pick up you pick up the splits and then you basically sum them up, right, by total number of nodes, and you add them up and you get the actual weight. So interpretation of this weight is the weight impurity after the split is 0.5 0.40 lower than the split last one. Last one was which one? Last one, the root one, right?
Yes.
Last one was root one. So we are now basically getting better and better. So these are the total number, right? And these are the far left, and this is for the right. So what are you doing? You are basically left divided by the total number multiplied by the Gini, right? And then plus right divided by the total number and multiply by the right Gini, okay? And that's how you get, and this number 403 is what? That's your weightage for split Gini, right? That's how you calculate the Gini weight. This is the second step, right? Now the final step is that you need to gain, get the gain Gini, calculate the Gini gain. That you look at what was the last one, right? And what was the now. So from previous, you minus the next tree branch. You'll get all this clear because I'm going to put all this into a tree now, right? And so basically the split reduced impurity by how much? That much. So when we only calculated the Gini based on accepted and rejected, the probability was 50-50, right? Even Gini was very high. Then we consider the credit score. We still, impurity is still very high because we could only reduce by 0.63. So what we need to do now is we need to go to the next level, and we need to actually repeat this all what we did for all the other features. So we consider first the root, then we consider, what was the second node? What did we consider? First was based on accepted and rejected.
Yes.
What the second chart was based on?
Credit score.
Credit scoring, right? Now we have left with age, income, loan. We can pick up the next one, and then this will be done automatically by the algorithm, but you need to understand the background of it. So you compute for all of them and pick and split with maximum Gini gain. At some point, maybe you pick up a one criteria which may hit the Gini really, strong, and bring the Gini really down. And we understood that if we make the decision of the loan from the previous data based on credit scoring alone, it's not going to be very effective. We may need to consider other things as well, which bring the Gini down. And that's the maximum gain. So this is recursively the actually tree-based algorithm builds this. Are you understanding this? Yeah?
70%.
Good. I recorded it, by the way. You can go and see the previous discussion.
Very clear. Clear.
Did you get it? Yeah?
Yes.
Fully?
Yes.
Good. If not, it is recorded, you need to watch this again. Okay, so this is the first one, as we see on top. This was the first one we did, right? Remember that? Yeah. The classes of approved and not approved, right? And this is a mixed sample was 500. Right? Imagine there were 500 samples in the first one. Sorry, 500 samples, right? And then from those 500 samples, what we say, and this is another example now, not the last example, right? We say, repeating, right? So we got 500 sample, less than credit score, what? 650. Gini is 471, right? This is child 2. And then we say, let's now see how many of those 500 samples loan amount is less than 150K, right? And how many are those, and on the right side we say how many of those income is greater than 57K. So we try both. We try both, and we calculate the loan amount. Those are less than 150K, right? With Gini we got the Gini here is 0.57, right? And we still have 250 different classes. 250 different classes, right? And the other side we have 370 classes. We need to get the classes 0, 0 at the bottom. You see here, there's a label data, classes 0, 0, right?
Yes.
Yeah. And then we got a classes 1, 1. So we gotta go to class 1, 1 side, and that's the lowest Gini, isn't it? If you look at the, what criteria you need to pick up that has the lowest Gini? What criteria has the lowest Gini here? 0.28, right? That means that data is close to purity.
Yeah.
So based on basically loan amount and credit score, right? Those things, you can actually come down to a closer decision, right? And but if this 1-1 class means it's still mixed data, but majority of it is approved. What I mean approved? So majority of it is approved on the right side, but still it's mixed data. Now let me give you another example of this. Look at this tree. This one actually explains you everything. Now if I can get your attention for 5 minutes, right? You won't have to pay attention again, right? Build the tree recursively. So you need to understand what are all the features that you need to know are on this slide. This is the most important slide, right? So you remember the first one we did is accept and reject,
Yes.
right? After that we did the credit scoring, less than 650. Gini was 471. Sample we were able to reduce from 1500 to the 500, right? And still there are like different classes there, right? What it tells you that this is a credit score based split, right? Application with that credit score on the left side and those with the right credit score, and this is what we did in the last one, right? There, left and right box, previous slide. And Gini was 0.74, means this node is somewhat mixed both, and samples are 500. About 450 are approved and 60 are rejected. So how many ones are there? 450. So out of 500 we picked up what are the approved ones, right?
Yes.
So 450 are 40 are approved and rest are rejected. So in the class it says 1 are how many? 1 means accepted, approved, right? 440. Got it? Okay. Then what we do is we look at the second one and then we say now this is another child here, right? We say where the income amount is less than, loan amount is less than 150. Now this split checks the loan amount whether the requested loan is less than 150, right? And we calculated the Gini based on that is 0.5. And class is 250, which means 250 were approved and rest was rejected. Okay? And if we tune it onto income greater than 57K, our Gini is slightly higher than this one, right? And sample we get it is 630 and the class is 370, which means 370 approved. Rest are rejected. If you go further down, and this label mean that you have, this is another representation. I mean, you could pick up any other one. To label basically your predicted class, the same way we did on top, which was based on income and based on credit score. And you get a 290 sample. 0, 0 mean is still mixed data. Majority of is rejected, right? And then you go further down here. Gini is 0.37 and 0, 0 class. 0, 0 class means both categories are nearly equal now, right? Both classes are nearly equal. 0, 1 mean, 1, 1 mean both classes are nearly equal, but majority is approved. Both classes are nearly equal, majority is rejected, right? And Gini is here, this, and similarly we keep dropping it here, showing model successfully. Now here, the lowest Gini is on this branch, right? Here. So the Gini drops from 0.7 Did it drop from 0.72? That's the greatest drop, isn't it? So we got our purity here. So which means this class, whatever we used here, right, is working. Okay, it's really dropped from, because when you use the loan amount, okay, less than this, it didn't work. Then we use the loan amount less than this, Gini was still higher. But then we use another class, okay, Gini was really low, so that's where our final hook is there to give us the right thing, right? In an example of, it's like this branch is more like, is it raining? Yes or no? You know where glasses, what are the probability of which glasses you will wear? Very hard for me to tell, right?
Yes.
But if I know it's raining and then go to another child, is it sunny or not? If it's sunny, I know you're going to wear shade. If it's not sunny, I know you're not going to wear, you're going to wear maybe, clear ones. So this is how you do it. So class 1, both means approved and rejected appears in the node mix, but most of them are on the approved one. And similarly, all the information is given. This is how the algorithm works in the background, alright? Which algorithm? Any decision tree based algorithm. And what are those? Random forest, yeah? Gradient, and also SVM is SVM tree based?
No.
No, it's what is based? Vector based, right? So, and that's how it basically do the prediction. Now, this is the second last one. So first one was root 1, right? Root 1 was 471, right? We got the root 1, and then from root we went to the first child, purer income split. Then we did that based on income, right? This is income split. It's purer than this one, isn't it?
Yes.
Yeah. And then we go further down, and it keeps bringing it down and down and down. And you go child 2, child 3, you go to the leaves, which give you the Gini closer to the 0, right? Now, this is the whole theoretical background to it. Now what you need to do is you need to understand the lab. And I have put there, I'm going to put on LMS, the lab, and by going through the lab, you'll be able to understand that how to explain the core idea of decision tree, key terms, feature, target, split, impurity, Gini, entropy, leaves, these things are already explained. And then build a loan approval data set, understanding each feature and target, prepare data set, handle missing values, that's there in the code, right? And also train, evaluate baseline decision tree, and again calculate what? Accuracy, precision, recall, F1 in confusion matrix, right? And then visualize the interpretation decision tree, you can plot it there. Actually the way I did that. And then diagnose the overfitting, underfitting by looking at different features and cost complexity. There's another CCP alpha to simplify the cost of it. And then you can tune a little bit more to get a better accuracy. And all of this is based on, basically, and this is the last slide, is here. So I'm going to give you this PPT with this slide, and I want you to basically go and try it yourself. This is a loan, where is it? Is it gone? Here. Yeah. This is a data set, and if you look at it, right, it's very well commented. It tells you everything. I want you to, for homework, I want you to go through it, right, and understand, keeping in mind what I covered in the lecture. I just want you to, I don't want you to learn the code, but I want to understand the concept. And I want you to be able to, for example, if you tune this, few things there, for example, here, if you go further down, this is just a data set generation, right? If you go further down here, you're basically doing the first plot of based on approved and rejected, right? So these are approved, these are rejected. First one, so first split. And then you go on the second split, and here you can pick up the feature that you want, and then you can plot it again. A model, you can train the model, and then you can calculate the precision and accuracy and everything based on that model, and then you can create a confusion matrix same way, and then visualize the decision tree. So here is actually this is a little bit code that basically put your decision tree based on the model, right, that we used. And here you see here, yeah. So basically your and these the way to read these ones are class 1 and class 2. How many class 1 and how many class 2? Within the bracket you see here values. This is class 1 and this is class 2. This is class 1 and class 2. Class 1 and class 2. So you're going to look at, like, on this level you get around 0.34, and you may have to go further down to bring, and this is done by the algorithm, not manually, right? This is done by the algorithm using the same concept as they were there, right? So I'm going to stop it here, and I'll let you to see that. Right, so